In the last presentation, we have seen the working of web. With the help of web, how exactly key stream is generated, and with the help of key stream, how the encryption takes place and as well as the decryption takes place. So to reiterate that, IV, initialization vector, and actual key are concatenated with each other. They are given as an input to RC4 algorithm. RC4 algorithm spits out a key stream which is XORed with the plain text message to derive a encrypted text message. This is the process for encryption. Same process in reverse order is used for decryption. Like again, IV and key stream. IV is a part of packet which goes as a clear text in the packet. So IV is known to the receiver. Key is also shared between receiver and transmitter. It's a shared secret. So with the help of IV and key, again receiver will find out the key stream which is identical to the transmitter's key stream. He has an encrypted text message. He will XOR that encrypted text message with the key stream to get a plain text message. That's the working of web. Now what are the problems with the web is the topic of this slide presentation. First problem is there is no key management. All the devices which are using the web will be using same key. All the devices, I mean the devices which are connected to the AP, the devices which are part of that BSS have to use same web key. There is no process how to change the web key. The web key has to be manually changed by the administrator on access points as well as all the clients, and the process is manual, which creates a hurdle in changing the web keys very frequently. Web as a standard doesn't mention any key management or key changing procedure. That's one very big problem. Consider an office in which wireless is deployed. A single AP is serving say 10 clients. 10 clients includes your senior management, your programmers, and your admin and HR and everyone. Now if everyone is actually transmitting their packets on wireless side and the AP is using web and the same key is used by everyone, it is more or less that everyone knows what packets are transmitted by HR department, what packets are sent by administration, what is finance, and which is very scary. Anyone can decrypt anyone's packet. It is clear text, as good as clear text, because everyone knows the key. The only thing that he has to apply is find out the key stream. IV is known, key is known, just XOR and find out the clear text message. So insider attacks are very easy with no key management. Second problem is key stream must never be reused for security. For ideal security, the security lies in the key stream. The key stream for every packet, if we generate a different key stream, it is very good way to be secure, but it is not possible because IV space is very small. IV is just 2^24, which is very small number. Believe me, if say 5 to 10 clients are associated with the AP and they are doing some data transfer, some HTTP transfer, some file transfer over the wireless, within few hours this IV space will wrap around. And once IV space wraps around and the same key stream is used again and again, it is very easy to find out the key stream itself, because the dictionary attacks and some statistical attacks can be applied over the packets, and the key stream can be easily derived and the key also can be easily cracked. The next problem with the web associated is IV just 24-bit and transmitted as a clear text. The IV or initialization vector is a part of IEEE 802.11 packet. It is inserted at the end of the MAC header and it is inserted as a clear text message. IV is never encrypted, and the key stream is generated with the help of IV plus key. Now 24 bits of the key or the seed are known to everyone, which is very scary and very dangerous for any encryption algorithm. Next problem is no standard procedure for IV generation. Standard IEEE 802.11 standard doesn't mention any procedure for generation of these IVs. So most of the devices generate these IVs as increasing order, 1, 2, 3, 4, 5, 6 and so on. So if at a time AP and client is restarted, there is very good chances that AP as well as client will start transmitting with IV1, 2, 3 and so on. So the IV space collisions are very easy to generate. One more problem with WEP is first few key stream bytes are predictable in RC4 algorithm with the weak IVs. Now the implementation, the way RC4 algorithm is implemented in WEP is flawed, and because of these flaws and the weak IVs going clear text, there is one very famous attack, FMS attack, and according to that FMS attack, there are few IVs or initialization vector which are weak, which actually when these initialization vectors are used in the packet, the first few bytes of the key stream are predictable. Now in IEEE 802.11 data packets, first 8 bytes are LLC headers and the contents of LLC header are almost fixed. So we know the clear text message of first 8 bytes of most of the packets. So it is very easy to find out the key stream for those packets, and if the weak IV is also present, there is an algorithm in which the key cracking thing can be easily done. There are many attacks like FMS attacks, Corec attacks, known plain text attack and so on. Next attack possible with the WEP is bit flipping attack. What exactly done in bit flipping attack is few packets in the few bits in the packet are flipped and packet is retransmitted. Now a simple defense mechanism is applied in WEP against the bit flipping attack is a ICV or integrity check vector is present at the end of the packet, and integrity check vector is a CRC32 function. Now CRC32 being a linear function, if attacker changes few bits in the packet, it is very easy for the attacker to recompute the ICV. If only few bits are changed, the ICV byte recomputation is very easy. I will be creating a separate video for how this ICV recalculation can be done, but believe me, it is very easy to change the ICV with bit flipping attack. Why I am saying it is very easy, because CRC is a linear function and RC4 is transparent to XOR, and because of these two properties, bit flipping attack are very easy to perform. Okay, ICV uses CRC32 and ICV is good for noise detection. ICV or CRC32 is good for noise detection, but it is extremely bad as a cryptographic hash. It is as good as used as a cryptographic hash, so that it can find out whether the packet had changed or not. MD5 is a good cryptographic hash, but CRC32 is very bad because it is linear. So few bits changed here and there can be easily recomputed the ICV value or CRC32 function.